Good morning, everyone, or good afternoon, depending on where you are. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Here with us today, we have Dr. Mita Panu, a Senior Scientist at Orange County Water District. Today, Dr. Panu will be discussing a PFAS treatment study, which won an honor award in our research category of the 2021 AAEES Excellence in Environmental Engineers and Science Awards. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, you'll be able to type your question into the attendee chat panel on the left-hand side of your screen. Okay, let's get started. Welcome, Dr. Panu. Thank you for joining us today. We're ready when you are.
Hello, everyone. Again, good morning or good afternoon, depending on where you are. The topic of my presentation today is OCWD's PFAS treatment study. And as Marissa mentioned, our study won an honor award by AAEES, and we were invited to present here, and we appreciate the opportunity to be here and present our results. So before I get started, I just was informed that it's probably better to turn off my camera so that we have a better visual. So I'm just going to turn my camera off and then go back to the full screen mode. So hopefully you can all hear me okay. Again, welcome. And I appreciate the opportunity to be here this morning or afternoon, depending on where we are. So I'm going to start with the outline of my talk. Basically, I will talk about what is OCWD and what are the PFAS impacts at OCWD. Then I will touch a little bit on our study objectives. I will then share some results from our pilot test as well as our lab scale testing. Then I will provide an update on the construction of multiple treatment systems over here in Orange County. And again, what is the future research that we are focusing on in terms of PFAS as well as other related research. So before I go forward, I want to thank the team over here at OCWD, our research and development department, as well as other teams at OCWD, namely water quality team, the lab department, and our partners at Jacobs and Battelle, who basically provided support for our PFAS treatment study. And last but not the least, the media providers who provided us the media to get it tested at lab scale as well as at pilot scale. So what are PFAS? I think it's such a common topic that probably everyone know what PFAS is, but just to reiterate, PFAS are per and polyfluoroalkyl substances. They are composed of carbon fluorine bonds, and they are generally labeled as forever chemicals because they are so resistant to degradation in the environment. The most common PFAS that we hear about in the water sector as well as in the soil sector are PFOA, PFOS, and PFBS. And the reason we talk about these three PFAS more often than others is because a lot of regulatory attention has been paid to these three PFAS over the last few years. So going into the detail about what Orange County Water District is, Orange County Water District was formed in 1933 to manage Orange County's groundwater basin. And when we say Orange County Groundwater Basin, you can see a map on the right of the area that Orange County Water District manages. So we have a bunch of recharge basin or spreading ponds, and we are connected to Santa Ana River water. And then the blue highlight on the map basically shows our surface service area. This basin provides groundwater to 19 municipals and special water districts, which amounts to about 2.5 million residents. So OCWD service area is huge. It provides about 77% of water supply for North and Central Orange County. So, when we talk about PFAS, the most important question that comes to our mind is that what is the extent of PFAS impact in the OCWD service area? So, as you can see on my screen on the left, I put current California DDW's notification levels as well as response levels. So, as you can see, a lot of regulatory attention has been paid to three PFAS, namely PFOA, PFOS, and PFPS. So the regulatory attention, at least in California, started in about 2020, where DDW came up with these very low notification levels and response levels, which are like in nanograms per liter or parts per trillion. Although these NLs and RLs are not regulatory limits, they are not enforceable, but we know that DDW is working on getting MCL set up for these three compounds. So, in terms of impact of these regulations on OCWD, we know that 11 of our water retailers have been impacted by the P4 response level of 10 nanogram per liter, which amounts to about one third of groundwater basin production, which is a huge, huge number. Because of the PFOA limit, we had to close our wells and we had to get imported water, which amounted to about greater than $50 million per year. So we had to come up with a solution. So our solution was to find an adsorbent based technology to remove the PFAS and get our clean water and bring our local groundwater supplies back online. Because reliability on imported water is ending up being really, really expensive. So I wanted to show a map of the wells that have been impacted by PFAS regulations. So you can see all the colors on the screen. Again, if you're not from California or nearby, they may not make a lot of sense to you, but the idea to show this picture was that you can see that there are a bunch of wells and they vary from about 6 to 8 different cities. So we had to do something about it. So, before I go forward and talk about how we dealt with the PFAS problem, I wanted to basically describe that when we think about OCWD and people hear about OCWD, a lot of people start thinking about the OCWD's GWRS system, which is a partnership between Orange County Water District and Orange County Sanitation District. And GWRS is actually the world's largest water purification system for indirect potable reuse, where we get tertiary treated wastewater from OCSD or Orange County Sanitation District, and we treat it at OCWD using three-way process of microfiltration, reverse osmosis, and UV with hydrogen peroxide. And this water that we produce using GWRS system is PFAS free. So there is no PFAS in this water, which we use for indirect potable reuse, because we know that reverse osmosis is very, very effective in removing PFAS. So I wanted to get this message out there, because when we talk about the other water, which is the water that has PFAS, that is different from the GWRS water. So going back to the objective of our study, which we call OCWD PFAS treatment study, was to find an adsorbent that can best remove the PFAS, and it is also of best value. And by best value, we mean that we want it to be affordable for the water districts. So we tested various products at pilot scale as well as lab scale. And the products that we tested range from granulated activated carbon, ion exchange, which were mainly anion exchange resins, as well as we tested some alternative adsorbents. And basically, the pictures on the screen that I show here are real pictures of some of the products that we used in our study. Moving on to the list of various adsorbents, we actually tested 8 GAC, 4 IX, and 2 alternative adsorbents. And at the time when we conducted our study, we were informed that it is one of the nation's largest pilots that we did at OCWD in terms of number of adsorbents that were included in the study. So we included 14 different adsorbents. Again, this is for information only. I describe here the empty bed contact time and the suppliers who provided us with the products. And I basically describe here that these products were tested at lab scale as well as at pilot scale. Another thing to mention here was that most of the products that we tested in our pilot and lab study were single use resins, but we did test a product or two that were regenerable. Here again, some pictures of the resins. GAC is on the left, and in the middle it's IX, and then we have alternative adsorbents on the right. And the idea was to show how the size varies a little bit between the different products. So before I go into presenting some data, I wanted to just introduce the concept of breakthrough curves. So the idea is that when you have influent water that has PFAS, when it goes through an adsorbent, the adsorbent has a capability of removing PFAS. So it goes through the adsorbent, and the effluent water that you get at the bottom is PFAS free. Again, looking at the chart here on the y-axis, we have PFAS in treated effluent, and on the x-axis, we have cumulative volume treated or time. And as you can see here, if you have a new adsorbent, when you collect PFAS, when you collect effluent and test PFAS levels in that effluent, initially the PFAS levels are very low, but as the adsorbent gets exhausted, the PFAS level starts to rise, and it reaches a plateau when influent and effluent PFAS concentration are equal. So I wanted to bring this out here because when I show the breakthrough curves from our real data, you can get an idea about how the shape of the curve would be expected to look like. Moving on, I will start first with our pilot program. Over here, we show a couple of spreading ponds at OCWD. There is Warner Basin, and then there's Little Warner, and then there's Huckleberry Pond. So these are our spreading basins at OCWD. Here, OCWD is the field headquarters office, and the star here shows the Bessie well, which we selected as our pilot location to pilot different technologies. I also show here in the table mean concentrations of 5 different PFAS that have been found in OCWD's water. So as you can see, they can range from low parts per trillion, from single digit to about in the 20s nanogram per liter or parts per trillion. Again, just to keep the interest going, some pictures of our pilot program. We had constructed a prefabricated building and we housed the pilot inside this building. And the idea was to have a pilot program that can last a couple of years because we wanted to test technologies that are coming in the market as we go along in our program. Some pictures from the pilot skids that we included in our study. These pilot skids were generally metal skeleton frames, and they hosted multiple transparent PVC columns, and the products were either GAC, IX, and alternative adsorbents, as I mentioned before. Again, if you're interested in learning about the size, I provide the size of the skids here, and then the ion exchange skids were a little bit shorter. But again, it was a huge pilot program with 14 different adsorbents. Now, moving on to some of the results. Again, I will present the pilot results first, and then I will move on to some of the results from our lab study. So what you see on the screen is the performance of different GAC products. And on the y-axis, we have PFAS concentrations in nanogram per liter in the treated water. And on the x-axis, you have either the months that the pilot have been running, and you also see the bed volumes that have been passed through the resins. So as you can see here on the left hand side, I plot the bituminous GAC products, and on the right hand side, I plotted the non-bituminous GAC products. And what we saw was, generally speaking, the bituminous products performed better than the non-bituminous or blended products. And overall, Calgon F400 had the most superior performance in terms of removal of PFOA as well as PFOS. So as you can see here, the Calgon F400 is presented in orange here. And when we say that it was the better performing product, what it means is that it had the latest breakthrough as compared to the other 7 GAC products. Moving on to the performance of IX, generally speaking, Evoqua's PSR2 Plus showed superior performance for PFOA removal relative to other IX products. And if you look on the right on your screen, I plot 4 different PFAS, PFOA, PFOS, PFHXS, and PFBS. And you can see clearly that the pink line had the latest breakthrough, which shows the performance of Evoqua's PSR2 Plus. I also wanted to mention here that all the 4 IX products showed a later breakthrough of short chain, which is PFBS, and also a later breakthrough of sulfonates, which is PFOS and PFHXS, relative to the GAC products that we previously saw on the previous slide. I also want to provide a disclaimer here that adsorbent performance can be very site specific, and we saw that in our lab study. What that means is that if Evoqua PSR2 performed the best for our water quality, that does not mean that it's the best product out there. What that means is that it has great potential for PFAS removal, but the performance can vary depending on a utility's water quality. But for us, Evoqua's PSR2 Plus clearly showed better performance. Moving on to some of the results from the alternative adsorbents, we saw some encouraging results for alternative adsorbents Cetco Fluorosorb 200, which is shown on the right in purple. And if you compare the purple color with the pink and the orange, you can see that the performance is comparable to Evoqua's PSR2 Plus, which was our IX product shown in pink here. And then, of course, GAC also performed really good, but GAC could not outcompete the performance of IX as well as alternative adsorbent. So what we found was that since this alternative adsorbent, which was relatively new in the drinking water market, it merits consideration for full-scale treatment because of its superior performance. And later on, when I talk about the cost for different products, because we did do a cost analysis, we basically concluded that the alternative adsorbents, Fluorosorb, is also comparable in cost as compared to the IX products, so which is a good sign. Moving on to some of the lab studies that we tested multiple adsorbents in RSSCT, also called rapid small scale column testing. And this is basically a bench scale study where we tested the GAC as well as alternative adsorbents. And the advantage of having the RSSCT is the fact that you can get results or the breakthrough curves very quickly, and you can screen multiple waters using RSSCT. And the idea is to collect the water and take it to the lab and test it using these tiny columns. So the kinetics of breakthrough is much faster when we have smaller columns, and also the fact that the GAC media is crushed before it's filled into these tiny columns. So you can get some idea about how tiny these columns are as compared to the previous pictures I showed on my screen from our pilot study. So since RSSCT is a much quicker test, we were able to test 9 different producers or production wells in the Orange County area, and we tested 10 different waters. Again, some details on the RSSCT. We did this RSSCT in collaboration with Battelle, and it was based on constant diffusivity assumptions. And we have a lot of results because we tested 10 different waters. So in the interest of time today, I will mostly present results from PFOA. So before I dive into the results, I just wanted to show some nice pictures and keep the audience awake and interested. When we did the RSSCT testing, we basically filled these 55-gallon drums at our producer sites on the back of a pickup truck, and we sent these to our Battelle lab, which is in Ohio. So we did multiple rounds of 55-gallon drum fillings and sending them to the lab, which was a fun experience as well, in our opinion. So some pictures from the RSSCT-Lab Testing. Again, as I mentioned before, it's the Battelle lab in Ohio. This is a typical RSSCT column setup. You can see some pumps, and then these are the little columns. I'm sorry, these are the little columns that I showed before, and these are the flow meters to monitor the flow in these columns. So let's dive into some of the results. Again, we had a lot of results from this multiple water study, but just to keep things simple, I'm going to show you some results which were the highlight. So over here, I present results from Calgon F400, and we compared the virgin variety of F400 and the reactivated variety. Looking at the chart on the y-axis, you see water volume treated to reach 60% of initial PFOA concentration. And then on the x-axis, we have 4 different water producers having different water qualities. If we compare the performance of the virgin and reactivated, we generally saw that virgin GAC may have provided longer life with low DOC waters. And when we say virgin, it's the light orange product. So you can generally see that the bar for the light orange was bigger as compared to the dark orange. So we generally concluded that the virgin product performed better for our water qualities, but the performance varies by the quality of water for the producer. Moving on to some more results. Again, I'm presenting the results for PFOA only. And on the y-axis, you see bed volumes to reach 60% of influent PFOA concentration. And on the x-axis, we have 10 different producers. The different colors of the different bars are actually different GAC products. So the first observation that you can clearly see is that there is quite a bit of variability among the different GAC products in terms of product performance. But generally speaking, we saw that Calgon F400, which is the orange bar, and Evoqua's Ultra Carb 1240 LD, which is the purple bar, performed the best, generally speaking, among all the producers. Again, if you're curious about why we have a lot of products in the previous test and then less products here, what happened was when we started the testing and we tested one, two, three, four, first four rounds, we found that we don't even have to test all the GAC products because we pretty much identified the top few performers. So for the later testing, we focused on our top GAC performers versus testing all of them. Just moving on to more results, what we did was we found that Calgon F400 also performed the best as we saw in our pilot study. And we saw the same thing in our lab study, which reiterates our findings and confirm our findings. We also found that there is large dependency of GAC performance on producer water quality, particularly DOC levels. So what I show here on the chart is on the y-axis, I have effluent to influent C over C naught concentration. And on the x-axis, I show the RSSCT bed volumes. And generally speaking, the easiest way to read this chart is that whichever line is to the very left had the worst performance, and if the line is to your right, had the better performance. So we saw that the Bessie well water, which is the yellow color, had the highest DOC in the water, and thus it performed the worst. Whereas these bunch of producers who had a lower DOC in their water performed better for Calgon F400. So we concluded that there is large dependency of GAC performance on producers' water quality, and particularly it's the level of DOC that would change the product performance. Since we were really interested in the DOC levels, we also got interested in the character of DOC. So one way to look at the character of DOC is to use a technique called excitation emission matrix spectroscopy. And this is a method, again, it's a spectroscopy method to look at the different fractions of DOC. So what we did was we took different waters and we passed the water to the EAMS, which is a spectroscopic method, and we identified different regions using these heat maps. So if you pay attention here, these different Roman numerals represent different excitation regions in the water. And the first and the second region are aromatic proteins. Number 3 represents fulvic acids in your water. Number 4 represent hydrophilic acids. And number 5 represent humic acids. So what we found was that when we compared our Bessie well water with water from two more cities, Fullerton and IRWD, we found that Bessie well water had higher fractions of humics and fulvics, whereas Fullerton and IRWD had higher fractions of aromatic proteins, which led us to conclude that DOC character is a big contributor in determining which GAC media would perform better. because as you recall from the previous screen, Bessie well water had the worst performance for Calgon F400, and we concluded that the not only the magnitude of DOC would impact the it's also character of the DOC conclusion that we got from our study. So in the future, we think that whenever we want to test a new water, we feel that the EAMS would be an important measure because that would tell us the character of DOC present in the water. So, since we were so interested in the DOC character, we ended up doing a multivariate regression analysis, and we basically evaluated the effect of DOC, humic acids, fulvic acids, and aromatic proteins. So what you see on the screen here is on the left hand, on the y-axis, we have bed volumes to 60% exhaustion, and on the x-axis, we have the different producer waters. And what we found was that DOC and humic acids were significantly correlated with the data. So you can see how the regression line is so smooth. And what that means in simple words is that if we want to see the performance of GAC, we can pretty much collect a new water and check the DOC levels as well as humic levels, and we can predict which GAC would perform better for our water quality as compared to another water quality whose DOC and humic levels are different. So we feel that this regression analysis was really important conclusion from our study, because even before you do a pilot, you can have a very nice prediction of the fact that if Calgon F400 would work better for your water quality, or is it gonna be Evoqua's Ultra Carb. So that would be a really good tool to use in the future. Moving on to some of the results from the alternative adsorbents. So we tested two different alternative adsorbents. One of the important ones we identified in our study is shown on the left-hand side of your screen. And again, just to give some context for these charts, if the lines are towards your left, the performance is worse, whereas the more they are to the right, the performance is better. So for Cetco FS200, we saw that FLUORO is definitely superior as compared to the other alternative adsorbent that we tested. We also saw that there was little difference among the different producers. So one of the producer was right here, but all the others were kind of cluttered right here, which led us to conclude that the DOC that impacted highly on the GAC performance may not impact the performance of alternative adsorbents. And we also concluded that since Cetco FS200 has been proven to be highly effective in removing PFAS in our pilot study as well as in lab study, we should consider it for full scale treatment as well. Another interesting thing that we did as a part of our lab study was to study the impact of VOCs. I know VOCs is also a very important contaminant that a lot of utilities are dealing with. So we were interested in seeing if we select an adsorbent and DOC, if VOCs are present as a co-contaminant, would VOC compete with adsorbent sites with PFAS? So what I show right here is C over C naught on the y-axis and bed volumes on the x-axis. But the important thing to note here is that when we had VOCs, the performance of Calgon F400 shown in the light orange, here, versus if we didn't have any VOCs in the water shown in dark, we saw that the presence of VOCs resulted in worse performance of Calgon F400. Similarly, for Evoqua's Aquacarb 1230CX, we saw that presence of VOCs resulted in worse performance as compared to no presence of VOCs. So VOCs were identified as one of the co-contaminants that would affect the performance of GAC adsorbent in any treatment system. So moving on to identify if RSSCT studies that we did in the lab scale, were they comparable to any field scale application. So we compared RSSC to field scale for GAC as well as for alternative adsorbents. And what you see on the screen on the y-axis are normalized PFOA concentrations, and then on the x-axis we have the different GAC products. The blue color represent the performance of adsorbent in GAC, whereas the green color represent the performance of an adsorbent in the pilot study. So when we evaluated these systems at 150 days of operation, which is pretty much the initial breakthrough of PFOA, we saw that RSSCT exhibited a faster breakthrough in each and every product, which means is that the blue bars were always bigger than the green bars. And what that concludes is that RSSCT is not conservative when it comes to prediction of GAC performance. Moving on to another comparison, since we were really interested in the comparison of RSSC to field scale, we did the similar evaluation at 390 days of operation, which is a typical change out of lead lag, and then GAC products are pretty much exhausted at that time. What we found here was that RSSCT prediction and the pilot prediction were pretty similar, and we concluded that RSSCT is actually a really good predictor of full scale performance when we do the evaluation at a typical lead lag bed change out, which is pretty much when the bed gets exhausted. For fluorosorb, we also did a similar comparison, and we found that RSSCT was not able to predict performance of alternative adsorbents. We saw that RSSCT actually over predicted to about 2 times greater runtime than from the real pilot. So we concluded from here is that if we want to do some testing for fluorosorb, RSSCT may not be the best tool for determining product performance. We also did some generalized cost evaluation. Again, I don't want to spend too much time on the details on the cost evaluation, but what we concluded was that generally speaking, if you take the cost of capital as well as O&M, GAC was most expensive, followed by IX, and the cheapest one happened to be the fluorosorb, which is an alternative adsorbent in the market. So to conclude, we concluded that all the adsorbents can successfully remove PFAS to meet the California's water quality guidelines. But we also observed that bench and pilot scale testing was very, very useful because we found that some products lasted longer to remove PFOA versus other products. So there were clearly some winners and some not so good winners in our study. The third one, we concluded that there is definitely a large dependence of GAC life on the DOC concentration in the water as well as the DOC character. So it's really important for utilities to look at their water qualities before they decide on what treatment would be best for their utility. If you compare the RSSCT results to pilot scale results, it validates the use of RSSCT for GAC, whereas RSSCT were not very good in validating the results for alternative adsorbents because they predicted very late breakthrough for fluorosorb FS200 as compared to the pilot. Moving on to the last few conclusions, we also concluded that all four IX products showed later breakthrough of sulfonates as well as short chain PFAS. And it was a good conclusion to have, and it's pretty much what we see in the scientific literature that short chain PFAS can be removed better by the IX products. Moving on, alternative adsorbents, we did identify some good alternative adsorbents in our study, and in the end, for our cost estimate, we concluded that GAC was highest in cost, followed by IX, and followed by FS200, which is our alternative adsorbents. So now we have these really good conclusions. What should we do now? So, what we are up to right now is that we have completed our phase one pilot, which is shown on the left hand side. But right now, what we are doing is we are working on our phase two and phase three piloting. So, our pilot program is ongoing. And the idea is that we are trying to identify new and emerging products that are coming in the market. Here's a list of new products that we are testing in our pilot in case someone is interested. Um, I know everyone thinks about the fact that yes, we did get nice pilot data from this pilot testing, but how are we supporting our full scale media procurement using the pilot data? So, what I wanted to say here is that we thought that the pilot data was really crucial in selecting treatment system media because based on the bid pricing that we got, Evoqua's PSR2 Plus was predominantly selected for the first three treatment systems. So we feel that pilot testing was really useful in identifying a superior media for OCWD. I also wanted to show some nice pictures for the various full scale design projects that we are working on. This is in Serrano Water District, and this basically represents a small systems, which is either a single well or two well system. Again, yes, it's a two well system, which is about 3,200 GPM capacity. Another picture from Yorba Linda Water District. This is a centralized treatment, and we are treating about 10 different wells in this, and it has 25 MGD maximum capacity. And there are about 22 vessels in this system. So this system is almost ready and functional in terms of treatment. Again, another picture from Yorba Linda Water District. Finally, what I wanted to do was tell you guys a little bit about what else we have been doing at OCWD's research department in terms of PFAS. In addition to the pilot program, we have also been working on three different projects. The first one on the very left is a method development program for screening for total PFAS in water, and we have funding from Water Research Foundation. And the other two projects that we are working on were alternative methods to assess IX and alternative adsorbent performance at bench scale, as well as situ removal of PFAS during managed aquifer recharge. And we are trying to utilize permeable reactive barriers for that part of the work. Just a little bit on the total PFAS project. We are working with University of Notre Dame on this method called PIGGY. It's particle induced gamma ray emission, and it's again a Water Research Foundation project. So this is ongoing. And this is my last slide, and I appreciate the time and attention I have been getting. And if you want more information, I have the OCWD website right here, and my email is right here. In case you have questions, please feel free to email me. I'll be happy to answer any questions. Over to you, Marissa.
Excellent. Thank you so much, Dr. Panu. Now we'll take a few minutes to answer some questions. I see a few have already come in. If you have a question, just type it in on the left-hand side of your screen where it says attendee chat, and your questions will be answered as they come in. Okay, you see the first one from Brent?
Yes, just one second. Hi, Brent. So the question is, what are the various EAMS emission regions delineated? I think what you're asking, Brent, here is that how are these separated in terms of when we put a water through the EAMS, like what do they mean? So I had a slide on the and some pictures. Basically, there are different regions of dissolved organic matter. So if you um, Marissa, can you hear me?
Yes, it's okay now.
Yes, can you hear me? I'm sorry.
Yes, I can hear you now. You can go ahead.
Yeah, so I tried to answer the question. I don't know if Brent heard my response. I have a picture on the screen, and again, I think the slides would be shared with the presenters, with the participants. Marissa.
Yes,
Um,
that's right. We'll send out the recording and also a PDF. I don't see that you're sharing your screen right now, so we can't see the pictures though.
okay, let me just reshare. Just give me a second.
Sure, take your time.
So I think Shanelli had a question basically asking, will the slides be shared? And yes, they will be shared.
Yes, we'll have
Um,
them on the website by tomorrow sometime, the recording and the PDF. And anyone can always email me if they want to get the link for that.
right. And while that is getting loaded, Brent, I'll come back to your question if you didn't hear it. Let me take the next one. The next one is from Todd. It says, after adsorbent is exhausted, how is it disposed of? Is there a plan in place to keep PFOA from re entering the environment? That's a really good question, Todd. I think it's the burning question these days in terms of the 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 fate for PFAS for the environment. So for our study, since we are focusing on adsorbent based technology, the way it works is that we get an adsorbent, and then once it's used, it is taken away. And I believe there are two methods for disposal. One method is taking it to a landfill, but the more common method is incineration. So the idea is that the spent resin is taken back and it's incinerated, and the PFAS is destroyed. But I know that there have been some landfill disposals for that as well. Let's see. So Another question from Brent. Do you have a theory for why the reactivated carbon was less efficient? That's a really good question, Brent. Again, we saw very little difference when it came to the reactivated versus the the virgin carbon. But one of the theories that I have heard before is that during the reactivation process, the surface area is even more enhanced. So that can be one of the reasons that the more surface area is there, the more the capability for PFAS absorption. But as you can recall, we saw very little differences. The it wasn't a substantial difference between reactivated and the virgin. So I'm gonna go back to Brent's previous question because I have the the EAMS on the screen, the heat maps. So let me take it to full screen. It's just taking its sweet time. So while that one is loading, there is a question from Bill Butler. And the question is, how is IX regen backwash water managed? So in terms of IX, Bill, there is no backwash needed for IX. So once a fresh IX product is brought in, it is loaded as is, and no backwash is needed. So we don't have to manage the backwash in that case. Let's see. So the next question is, so no regeneration, replace and dispose, assume that was considered in the cost. Yes, that is correct. The cost that I presented here today was including the cost for the vendor to take the material away and also um, take care of the disposal. The next question, again from Bill, was reactivated carbon usually has residual organics from initial uses that cannot be removed during regeneration, which reduces its absorption capacity. I think that was more of a comment versus a question. Wendy, thank you, Wendy, for the kind words. The results of your GAC pilot look promising. Do you think GAC will be cost-effective treatment option for OCWD? That's a good question, Wendy. I think I presented the cost. And
Oh, we might have lost her again. Okay.
can you hear me?
Yes, now I can hear you.
Okay, I'm sorry. I must have been having
That's
some
okay.
connectivity issues. So Wendy had a question. She's asking if the GAC would be a promising treatment for OCWD. And we found that GAC wasn't the most effective treatment option for OCWD. And that is the reason that a lot of our producers ended up choosing IX versus GAC. But GAC is definitely an option for some producers. Again, cost wise, at least for OCWD, IX was more competitive as compared to GAC. Assuming you can still hear me, Marissa?
Yes, we can.
Okay, perfect. Shawnee had a question. Was backwash performed on GAC? And if so, was PFAS measured on the backwash water? So we did not let's see, was backwash. I think your question is related to if backwash was performed on the pilot GAC, or maybe you're asking about the full scale treatment. Okay, yes. So we did perform backwash on the GAC because that was one of the requirements, but we did not measure PFAS because the time it was performed, it was a fresh media, so it was a brand new media, so we didn't expect any PFAS on the fresh media at that point. We also performed a backwash on one of the alternative adsorbents as well. But again, it was done at the very beginning of the study, so we didn't expect any PFAS in those backwash samples. Let's see. So I see another one from Wendy. Your results showed good P4 removal. Are these removals expected to be repeatable, effective at full scale level? Yes, Wendy, that's a really good question. I think the answer to that question is that we expect good P4.
Okay, we're having some connectivity issues. If we didn't get to your question, feel free to email me and I can put you in touch. Thank you, everyone else, for the questions we did get to answer. And thank you, Dr. Panu, for sharing your knowledge with us today. If anyone has any additional questions, like I said, email us. Our next event will be our annual awards ceremony and conference and will take place on Thursday, April 7th at noon Eastern. This event will feature keynote speaker Dr. Glenn Diger, a professor at the University of Michigan in the Department of Civil and Environmental Engineering. Dr. Diger will discuss the Clean Water Act for its 50th anniversary. You can go to aaees.org to our events page to register. And just a reminder, if you're not yet an AAES member and you're considering joining the Academy, please email me to discuss our membership options. My email is mwaterman@aaees.org. We'll have a recording of this event up on our website by tomorrow and also the PDF. That's all for today. Thank you so much and have a great day, everyone.
Thank you.